So yeah, I'm going to tell you a bit about cadmium and zinc cycling in the oceans, where it is the most important, how it happens, and then maybe why we care. Also going to talk a bit about isotopes, and well, as the picture sort of suggests, like it focuses a lot on the Southern Ocean, and I'm going to try and take you through it, hopefully not confusing everyone by doing two metals at the same time. So to start off, I thought, well, I'd talk a little bit about trace metals and nutrients in general. So I'm sure most of you are familiar with, the macronutrients, phosphate, nitrate, and so on, that are constitute about 95% of organic matter by mass, and these are really generally limiting productivity throughout the ocean. However, like in recent years, people have started to look at these trace metals down here. So these are a lot more scarce in the ocean, and they're also less required by phytoplankton. But considering that they are less scarce, they are about equally important. So on this diagram, you see the macronutrients plot along this line, and anything below this line would be limiting, anything above this line would be in excess. And you see that a bunch of these metals, they have quite a large range depending on where you are in the ocean. Most popular, I'm sure everyone's familiar with iron, which has a very prominent biological role. There's also others like zinc and cadmium, for example, which are the two that I'm going to focus on today. So I'm going to start off introducing you a little bit to cadmium, which has been first measured in the late 70s, early 80s by Ed Boyle, Ken Bruland. These are the first profiles they measured in the North Pacific, and you can, data is like, it's hard to see here, but this is cadmium up here, and then you have phosphate down here and silicate. And you can sort of see that cadmium looks surprisingly similar to the phosphate profiles. If we take a newer data set, this becomes a lot more obvious. So cadmium's in black and phosphate in green. This is also in the Pacific, this profile. And you can see that cadmium shows a close relation to phosphate and nitrate as well, because they both look very similar. And so when the first people measured this, they sort of interpreted this as, this nutrient type profile. People were thinking about this one-dimensional cycling associated with the biological pump, where you have uptake in the surface, then you have consumption and regeneration below, and then you sort of have some deep ocean where there's not all that much happening anymore. And you can see these features in the profile as well. You have a low surface concentration associated with the surface uptake, then you have an increase below towards a maximum at intermediate depth. That would be the regeneration part, and then you have anything below 2,000 meters, really very little is happening, relatively independent of this surface biological pump. So for cadmium then, people started looking into this, like why is cadmium drawn down? I'm sure many of you know cadmium is considered toxic for us, but also studies show that it's toxic for phytoplankton. So why do we have this nutrient type profile? And it was only like a couple of years later that studies showed that cadmium can also function as a micronutrient, only under certain conditions where it could possibly replace zinc in specific enzymes, for example. But so to this day, this is still somewhat of an open discussion, and this is a bit of a maybe. Some people claim that cadmium is taken up invariantly because it's also a 2+ metal. So anything that in the surface that requires two metals would take up cadmium as well. So while this has been suggested for 20 years now, pretty much, there's still an open discussion, and we still don't really know why cadmium is taken up to this extent. So then again, coming back to this first study from Ed Boyle, these are from the three profiles he measured. You could already see that there's sort of this, it's not quite linear, so a somewhat non-linear relationship between cadmium and phosphate. With again, it becomes more obvious if we use more recent data. So this is the Pacific section again, and you can see that the low surface concentration plot at the lower end here, both for cadmium and phosphate, and they sort of form one trend, and then everything below the intermediate and deep ocean plots on this upper line up here. And so this was pretty exciting because phosphate, as you know, is a major nutrient, and if we have something that correlates with phosphate in such a nice way like cadmium does, if we find an archive where we preserve cadmium, we could potentially use it as a proxy to reconstruct past ocean nutrient distributions, which would be pretty interesting. So this was the small introduction for cadmium, and I'm going to jump over to zinc. I'm going to keep doing this and hopefully not confuse everyone. Well, the takeaway from the cadmium part is it's possibly a micronutrient, but it definitely has this nice correlation with phosphate. And for zinc, we definitely know this is a metal micronutrient, and maybe some of you know this is also important for every one of us, for example. So zinc is used in a lot of enzymes across the biosphere, not just in the ocean. Very prominent is the carbonic anhydrase for conversion of CO2, for example. And again, going back to this first study from the 80s from Ken Bruland, so unsurprisingly, since zinc is so important for all the phytoplankton in the surface, again you have these nutrient type profiles with surface depletion and then an increase with depth. However, somewhat surprisingly, it correlates with silicon this time, not with phosphate. Again, this becomes much clearer if you look at newer data, though it's more obvious in this one. So silicon and zinc are the two that pretty much fall together, and then phosphate sort of does something different here. So this is especially apparent over here, for example. So even though it is obviously a metal micronutrient, it seems to be cycled on somewhat of a different scale than phosphate, which is maybe what you would expect on the first order. And then people looked into this further. So culturing studies then showed that only 1 to 3% of the zinc in diatoms is located in the opals or in the zinc and the silicon shell of these diatoms. And then if you look at the synchrotron XRF studies, you could see that the zinc is actually located together with the phosphate. In this one, for example, you can see it shows up in the same spots, while silicon is everywhere else. So this doesn't make any sense if you look at these profiles in just this one-dimensional biological pump sense. Like if zinc is located with the phosphate, why on earth would it look like the silicon in the end? You would expect if you regenerate the organic material somewhere around this depth, this is where you would think zinc should come out as well. So this linear zinc-silicon correlation that you get out of these measuring lots of these profiles and this somewhat messy zinc-phosphate correlation doesn't seem to make any sense if you look at it in a one-dimensional way based on the culturing and the XRF studies. So, well, this is from a recent paper from Derek Vance, and this is pretty much 40 years later since they first discovered it. So this has been like an issue or like a topic of discussion and confusion for a few decades now. So it's not something straightforward. So what is going on with these two elements? For one of them, for cadmium, we have this, not sort of kinked relationship, though it seems to correlate very well with phosphate in a one-dimensional profile. So that is somewhat confusing. Also, we don't know why it's taken up. Why does it even look like a nutrient? For the other one, for zinc, we have this nice correlation with silicon, even though we would expect it to correlate with phosphate, because that's the one it's located in with the cells. So there's really these are not just one-dimensional profiles, these are considering the whole ocean basin. And the question is then, how can we relate these sort of graphs to one-dimensional profiles? And what, if we look at things on a basin-wide scale, what about other marine processes like oceanic circulation, for example, that do really affect large areas? And if we look at the global ocean circulation, pretty much the first thing you run into that is really central in this is the Southern Ocean, which sort of sits at the middle of this cartoon. We have the Atlantic, the Pacific, and the Indian Ocean here. And you have this, should go this way around, the ACC, so this Arctic circumpolar current that goes around Antarctica and that connects the three major ocean basins. So this is one physical aspect of like the central role of the Southern Ocean. And secondly, well, it is a circulation, so starting somewhere is somewhat tricky, but if you would choose a starting point, you can see that a lot of these intermediate water masses do originate out of the Southern Ocean. So it's an important area for water mass formation. So if we zoom in further into this one, just to simplify things, because this circulation is rather complicated. This Southern Ocean hub where everything gets transferred through is actually, in terms of circulation, relatively simple. So this is following the Sarmiento paper from 2004, which has really been on the forefront of all of these discoveries of nutrient and trace metal distributions in the ocean. And so we have Antarctica on the left here, well, or in the south. And then you have this Antarctic zone where you have this Antarctic circumpolar current. And in this zone you have pretty much an Arctic surface water that sits at the top. You have upper circumpolar deep water, and this one brings nutrient-rich deep waters up from the deep ocean towards the surface. And then below that you have lower circumpolar deep water, which pretty much just sits there, doesn't do very much. And if you go further north, this is what I also showed up on this cartoon here. You have these red intermediate water limbs that originate here, they get subducted and flow out of the Southern Ocean. And apart from this circulation, this specific circulation here, you also have the biogeochemistry that is quite specific in the Southern Ocean. So even though you bring a lot of nutrients up from the deep ocean, you're limited in the surface waters by iron and by light. So productivity here is not as high as you would expect it to be based on nitrate or phosphate, for example. And so the surface Southern Ocean is one of these high nutrient, low chlorophyll zones. And it's actually the biggest one. So here iron limitation is really key to a lot of the processes that happen. Yeah, that's what I just said. So what I did in my PhD was really look in more detail at this Southern Ocean and what happens there. So I worked on two cruises. One is the Antarctic Circumnavigation Expedition, which circumnavigated Antarctica, unsurprisingly. And I was working on two of the legs, one starting in Hobart in southern Australia, and it goes down to the continent, and you go back up to Chile up here, and then you cross the Atlantic. And there's another leg from here to, well, over here, back over here, for the Indian sector. So the idea of this was to give us really a good idea what's happening in the Southern Ocean to those trace metals, which processes dominate under conditions where iron is limiting, and then if any of these things that happen there are actually exported out of the Southern Ocean with these water masses. To do that, I had a second cruise to look at, which was this GP19 from Geotraces, which again starts in the Southern Ocean and goes all the way into the low latitude to the equatorial Pacific. So really we could trace what happens and then how does it go out into the ocean. Just a very brief slide on methods, how we do things. I don't know how familiar everyone is with this. So, well, initially we collect seawater on a ship with these trace metal clean rosettes, and you filter the water. Obviously you're on a big rusty ship, so sampling is not trivial, and that's one of the main reasons why trace metals have only been done in, well, the last 40 years or something, because before you just pretty much sample either your equipment or the ship. So but it has become a lot more standardized, mostly thanks to the GeoTraces program, and yeah, you can do pretty nice things now with it. So after we have collected our seawater sample, the first step is to extract the trace metals. So we want to get rid of all the salt mainly. And to do this, we use a resin that chelates the metals, but none of the salts, or almost none of the salts. And then you would elute the metals from the resin, and you can discard the rest of the seawater. This is pretty nice. The next step is you want to clean up the metals you are interested in. So you would do some ion exchange chromatography. So if you want to measure things on an ICP-MS in the end, you'll have interferences, and you really want to get rid of anything but cadmium, for example, before you measure it. And that would be the last step. Measure things on a Neptune ICP-MS multi-collector, and you get your both concentration and isotope data. In my case for cadmium and zinc, but this is the same method also works for iron and in principle many other metals as well. So for those of you who are not that familiar with isotopes, I picked cadmium as the easier of the two systems to give you a short overview. So, well, as I said, cadmium has this nutrient type behavior where you have low surface concentration and then it's increased towards the deep ocean. If we look at isotopes, cadmium has 8 stable isotopes, and we typically report everything in delta 114 cadmium. So this is always a deviation relative to a standard that someone at some point picked. And I'll show you some typical signatures that we would expect in the ocean. And for cadmium, the thing that makes it relatively easy is that cadmium is mainly associated with biological cycling. So there's not, if you look at iron, for example, there's about 1 million processes that could affect it, and it gets a lot more tricky. For cadmium, in the surface where you have the depletion, you have heavy values, heavy isotope values, because phytoplankton preferentially take up the light cadmium, so in the seawater you are left with the heavier fraction of the cadmium. Oh, sorry. Then below you can still see some elevated values. These are associated with intermediate waters. And then if you go further down below 1,500, 2,000 meters, you can see everything pretty much stays on this dashed line, which is the deep ocean average. Nothing really happens anymore. So this is just a brief overview, what we expect to see or what we would like to see in the Southern Ocean as well. So coming back to this Southern Ocean hub, so we want to focus on just this side, just to simplify things. This is this iron limited zone where we have a deep supply of nutrients, and just want to look at one cadmium and cadmium isotope profile in this region. So cadmium is on the left, cadmium isotopes on the right. We only go down to 1,000 meters, and you can see, well, this doesn't, this goes down to like 5,000 meters or something, but as I said, nothing really happens below here anymore because it's all the same water mass. So we want to look at the top 1,000 meters where you have this upwelling, where you have surface processes, where things are happening. And starting at the top, this is pretty much repeating what I just said as the introduction for cadmium isotopes now, just because, yeah, they're relatively simple. In the surface, you have a depletion of cadmium, and this comes with heavy isotope values up to +1 per mil. If you go below into the subsurface, you have this upper circumpolar deep that it brings a lot of nutrients, and with that also cadmium with it. But if you remember the biological pump, the one-dimensional cycling, you would also expect anything that's been taken up in the surface would regenerate somewhere around this depth again. So you would release cadmium. And since you take up the light cadmium in the surface, you're left with the heavy in the surface, you would expect a light remineralization at this depth. However, we see this cadmium maximum is pretty much like anything below. There's no specific light signal or anything. And we attribute that to the upwelling of this deep water that really brings a lot of cadmium, that is about plus 0.3 per mil. And then if you put the two together, you end up with something from plus 0.2 to plus 0.3, so somewhere in this gray bar, which unfortunately is pretty much what anything below looks like. So since you have two opposing signals here, you don't really see the regeneration or the upwelling specifically, just because they sort of cancel out. But overall, this is relatively simple now. So, and if we do this again for the whole Southern Ocean Basin, for this iron limited zone, if we look at cadmium against phosphate and color it for cadmium isotopes, you can see that Antarctic surface water is down here, has the highest isotope values. And if you go below, you can see, well, anything below upper circumpolar deep water is pretty much blue. It has all the same value pretty much. And you can attribute that to what I said. You have uptake and you have regeneration again. It's relatively simple upper ocean biological cycling at a very shallow level. However, you can see this is quite a steep line, and it doesn't look like what I showed you earlier for the Pacific. So here you have quite a strong cadmium depletion relative to phosphate. So if you go from the deep waters, phosphate is about 2.2 or something, and you go to 1.5, while cadmium goes from, well, 0.9 down to 0.2. So you deplete quite a lot of the cadmium over the same area, or the surface area, pretty much. So this is actually pretty systematic throughout the Southern Ocean, both for concentration relative to phosphate and the isotopes. So that's why cadmium is like a good example to start with. I'm going to jump over to zinc now and see what happens there. And so again, same area, this iron limited Antarctic zone, where you have the upwelling deep waters. And you can see that zinc again is depleted in the surface ocean, and you have a heavy isotope signal as well, again associated with the uptake. However, it's much smaller than for cadmium, so you go from, well, 0.45 in the deep ocean to maybe 0.6 or something. So even though you deplete quite a large amount of zinc, the associated isotope signal is, well, disappointingly small, so to speak. Then below, again, you would, if you take up light zinc in the surface, you would expect it to regenerate somewhere around this depth. First of all, the fractionation is small, and then we don't see any signal here. Like this, just like it's a straight line going down to the bottom. And this is mainly because a lot of the zinc again comes from this upper circumpolar deep water that upwells and brings this constant signature with it. So you don't have enough leverage, since the fractionation is so small, to really deviate. And then again, the lower circumpolar deep water is always pretty boring. It pretty much stays at the same values, both in concentration and in isotopes, just because it doesn't really interact with anything above. So again, if we look at this for the whole Southern Ocean, like for this whole Antarctic zone, this looks fairly similar to what I just showed you for cadmium. Again, this is zinc, this is phosphate, colored for isotopes. And you can see the surface waters that are low in zinc show the heavy values, while below the deeper values you can see a bit more, like it's a bit more colorful, not such a nice rainbow scale within the plot here, but the deviations are much smaller. So again, this is very systematic. Well, compared to these profiles from the North Pacific, where I showed you that zinc correlates with silicon, this doesn't look like that, does it? Like, this is pretty much a straight line, zinc against phosphate, so you cycle zinc with phosphate in the Southern Ocean, which pretty much agrees with both the culturing studies and those synchrotron studies that said zinc in cells is pretty much co-located with phosphate. So if you take it up in the surface, once you release it due to regeneration, you'd expect actually this, not what happens in the North Pacific. And again, just like for cadmium, you can see this is a very steep line or gradient, and actually even steeper, and you can see you deplete zinc from 6 nanomoles down to 0.5 or something, so you deplete almost all the zinc just in the surface here, while phosphate again goes from 2.2 to 1.5 or something. So this is mainly attributed to the limitation of iron, so because you don't have enough iron, other metals sort of jump in and help out, like zinc, for example, in different enzymes. And you have this strong depletion of zinc in the surface ocean. So this is just zinc and phosphate and cadmium and phosphate both in the Southern Ocean, just to show you how similar those two are actually behave within the Southern Ocean. Very much unlike to what I showed you in the beginning for the North Pacific. So for both you have this nice linear correlation between zinc and cadmium respectively against phosphate. Just because you cycle both very similarly over different depth scale, over the shallow depth scale of the surface Southern Ocean. So, and to confuse you a little maybe now, this is again for the Southern Ocean zinc against silicon, just because for the global ocean we have this nice linear correlation between zinc and silicon. So how does it look here? See, we don't really have this. So you can see that surface waters are slightly below this correlation. So we actually take up more zinc than silicon. So we go down from the correlation. Then as we go down in depth here towards this upper circumpolar deep water, we see that the zinc that we've taken up in the surface is regenerated at a much shallower depth than the silicon. Pretty much what we actually expect, again, from culturing studies. And then the deeper we go, the closer we get to some deep ocean value that lies on this line. So there's two things to take away from this diagram now. First one, both zinc and silicon are drawn down to very low levels within the Southern Ocean. So unlike the phosphate, which stayed very high, silicon also reaches similarly low concentration as zinc. However, they are cycled over a different depth scale within the Southern Ocean. So you get not a linear correlation anymore. So now we know what happens here within the Southern Ocean. Question is, how is this relevant? Like, why do we care about this? And this is where these intermediate water come into play that are formed by subduction of surface water and mixing. So the question really is, are these signatures that we form in the surface ocean, these like strong depletions and the isotopic signals that are associated with it, are they just relevant for this area, or do they get sort of dragged down and carried out into the low latitudes, the equatorial Pacific, and so on? And again, I'm going to do this for cadmium just because it has the bigger isotope fractionation and it's easier to show, but you'll see it'll be quite similar for both elements again. So I showed you that surface waters here go down to maybe 0.2 nanomoles or something, and you get values of +1 per mil. And then as these water masses, like when they come up, they keep flowing northwards until you cross some fronts, Southern Ocean fronts here, where you start mixing to greater depth. And you keep depleting cadmium, so you take out the cadmium that is, you go from 0.2 to pretty much zero. Just because you don't have any resupply from below the further north you go, so everything that's there will continuously get stripped out, and because you mix it with the bottom, it sort of disappears as well. And this mixing brings some of these depleted surface waters down to these intermediate depths. And I'm going to show you for Antarctic intermediate water how these are formed during this process. So this is, well, we got isotopes on the y-axis and then 1 over cadmium concentrations on the x-axis. So any binary mixing, so between two end members, so for example the surface water and the upper circumpolar deep water, if it's a simple binary mixture, it'll just plot on a line, so like the line that's indicated here. And you can see that the station that we plotted here, it sort of curves above this line, so we see there's another component that affects these shallow depths where you mix a lot of the water. And again, we're coming back to this biological pump, the shallow cycling. Of course, everything that is taken up, that is stripped out in the surface, will be regenerated just below in the shallow subsurface. So anything here will always have a small regeneration signal. And we know regeneration is light, because plankton take up light, cadmium. So if we add cadmium, we go this way to the left, because it's 1 over cadmium, and we'll go down in isotopes a little, and we'll end up with something around here. So the signal contains both the depleted surface water as well as the regeneration signal, and we end up with a pretty characteristic signal both in this Antarctic intermediate water and subantarctic mode water that flow out into the low latitudes of the Atlantic and the Pacific. And they carry these characteristic signatures. So you can see the subantarctic mode water, which is shallower, has a heavier isotope signature than the deeper Antarctic intermediate water, just because it has more of this heavy surface water, depleted surface water. So consequently, concentrations are lower as well. So this is pretty important to know, because so the little bit geographically small region that cycles a lot of cadmium here then has quite a big influence on pretty much everything north of it. So if you think about that circulation pattern, these water masses go far into the low latitudes, and you pretty much conserve these signals, and I'll show you that now. So if we take a station in the Pacific at 30 degrees south, so much further north, outside of the Southern Ocean, in cadmium isotopes, you can still see these signals, these heavier signals in subantarctic mode water and Antarctic intermediate water. So even though they originate pretty far south, you conserve them like to 30 degrees south and even further, and you'll only start mixing them away at some point when other water masses become more important. But if you also consider that this is mostly lower circumpolar deep water, just by deriving water mass end members in the south, you can pretty much explain the whole profile here, which is pretty cool. So again, I'm going to show you this briefly on this mixing plot, isotopes against 1 over cadmium. And this is what we had in the Southern Ocean. So we have our upper and lower circumpolar deep water and some surface water, and we said this is pretty much biological uptake. It's just fractionation as cadmium is taken up, and we have some regeneration that brings it back down. So now if we take this GP19 section, which pretty much starts in the Southern Ocean and then goes out into the low latitudes, so all these surface processes here will not happen once you cross these Southern Ocean fronts anymore. And pretty much on this plot, so this is all the data from GP19, and we stuck on these water mass end members that we derived just from this orange cruise down here, nothing else. And again, anything that is binary mixing, so adjacent water masses, will just be a line. So if we put in lines between the deeper water masses to Antarctic intermediate water, you can see you can explain pretty much everything here from Antarctic intermediate water to subantarctic mold water above. Again, pretty much fits very well. And then above, so 300 meters and above in the low latitude gyres, you see you have again some biological fractionation. And I know this is 1/, so it's kind of hard to figure out, and this goes like down to really, really low concentrations. But you can see the arrow here is kind of flat, so you don't have this strong fractionation anymore. You start maybe considering that you probably supply everything from subantarctic mold water. You have very little influence of your biological uptake in these oligotrophic gyres, for example. So anything below 300 meters or somewhere around there will be simple, conservative mixing or nearly conservative mixing of water mass end members that derive in the south. And then in the very, very upper ocean, you have some cycling going on at really low concentration, but this really doesn't have any noticeable effect on what happens below. And we can see this in the cadmium against phosphate. So this is what I showed you in the Southern Ocean. Again, this shallow cycling neatly together with phosphate. And then this is what it looks like for this P19 section. So if you go from the Southern Ocean into the equatorial Pacific, this is what I showed you in the beginning. So in intermediate and deep waters, again, plot along this line, and sort of mixing between all of these can explain pretty much anything in the deep ocean, both for cadmium and for phosphate. And then you have this break in the relationship, and you see that it's only these depleted surface waters that come out of the Southern Ocean, and then don't really see much more of this deep ocean cadmium, because that just sits in the deep circulation. It doesn't come back up to the surface. So they sort of do their own thing on this shallow branch. And the shallow branch actually, as you can see, it goes from 0.8 to 0 in phosphate. So this will be mainly phosphate drawdown. As you go further north, you don't have a big supply of phosphate, so you'll draw down the phosphate. While cadmium, it's already very low. You can't draw it down much further. So it starts at, 0.05 or something, and you go to 0. So there is not much happening anymore, just because there isn't any cadmium to be cycled a lot anymore. So again, I'm going to jump over to zinc now, and it'll be relatively quick, and it's very similar again. So this is what we had in the Southern Ocean. Again, nice correlation with phosphate between zinc and phosphate. So very shallow cycling. And then we really were confused about this zinc and silicon correlation in the North Pacific. So we have, if we look at the Southern Ocean, so this is nitrate and this is silicon. You can see that the silicon is drawn down. If you assume that silicon comes up here and then waters flow northwards, this is drawn down very quickly, like you reach very low silicon concentration, while nitrate stays very high and it takes a lot longer to be drawn down. You can see this. So zinc will look like silicon. You have a very high drawdown of zinc. Well, so you have an upwelling peak here. This is the zinc you supply from below, and as you go north, so here, this way, you'll see the zinc disappears very quickly, while phosphate or nitrate sort of doesn't really do very much while you deplete like 3/4 of the zinc. And then you can see phosphate keeps continuing to decrease, and if you go further, they'll keep decreasing while the zinc has pretty much run out. And silicon does exactly the same as the zinc. There we go. And so if you look at cadmium, you can see it does a similar thing, but it sort of lags behind the zinc. So the zinc gets drawn down first, and then the cadmium sort of follows. So this is one of the reasons why people have suggested under iron limiting conditions, zinc will replace iron in different enzymes. Once you reach a certain point where you don't have enough zinc anymore, you will start drawing down other metals like cadmium, for example, that can maybe also fulfill this function. But it really is this. So the main difference between zinc and cadmium in the Southern Ocean is this sort of spatial difference in drawdown, because you can see that the pattern looks pretty much the same. It's just shifted to the right a little bit. And that is and because silicon also follows this zinc pattern, this is why you get different correlations. So again, this is what we had for zinc silicon within the Southern Ocean. You can see that it's cycled on a different scale, but this is driven by biological cycling. As soon as you move out of the Southern Ocean, you get this mixing in the upper ocean, especially during winter times. You have deep vertical mixing, and you can see that the deeper waters that have this zinc excess relative to silicon. So this arrow is also it shows deepening mixing, which happens as you go further north. So the further north you go, the more you go towards this, towards the dashed line, which is that global ocean average. Just because you can think about it, if you mix more of the deep water masses that are rich in zinc, they will start to completely take over. Because you deplete the surface waters in zinc, it's pretty much only the deep component that dominates this. So hope I didn't overwhelm everyone completely. But there's a few relatively simple messages to take away, I think. So cadmium and zinc both have quite similar systematics within the Southern Ocean, where you have this iron limitation, cycled together with phosphate in the very shallow surface ocean. However, zinc is depleted to a greater degree than cadmium, and also sooner, so as to speak, further south, which is really important. Also, zinc in generally just shows a smaller fractionation, which is somewhat counterintuitive, because you think if you draw down more zinc, you'd see the bigger fractionation. So for the first people who looked at zinc in the Southern Ocean, zinc isotopes like Derek Vance, this was a big disappointment. And these surface Southern Ocean processes are really important, both the drawdown in cadmium and zinc in terms of concentration, as well as the isotopes, especially for cadmium. These really set those end members that are formed in the Southern Ocean, and then dominate pretty much most of the low latitudes in terms of water mass mixing. So if you take anything away from this lecture, or talk, whatever, just take the blue message away, because this is really something that is important. If you go out of the Southern Ocean, this one-dimensional view, if you just look at one profile, you say, oh, it's uptake, you do regeneration below, and then not much happens underneath. You're really missing this lateral component that probably, as we've seen, shapes most of the profile rather than a very limited one-dimensional cycling. So Southern Ocean processes, even though they happen in a very small area geographically, they are really important for these trace metals, and together with water mass circulation, they really dominate maybe, 90% of the distribution of these trace metals and their isotopes, and also other elements. So silicon, for example, which is, again, this Sarmiento paper where a lot of these ideas come from. And so you can come up with these nice sketches where you have Antarctica and upwelling in the Southern Ocean, and so the arrow sizes represent concentrations, and the colors represent isotopes. And the top is cadmium, the bottom is zinc. And I'm gonna leave you with that, and thanks for listening. And If you have any questions, please ask.